Welcome to our training manual, Adaptive Management to Improve De-icing Operations. I'm going to have two videos, one about 15 minutes and one about 25 minutes. This is part one, the background and field study findings. This is a project that was funded to the Department of Bioproducts and Biosystems Engineering, of which I'm a part. My colleague, Bruce Wilson, in the middle of the truck there, is my co-PI. A professor, and both of us professors in bioproducts and biosystems engineering. Doug Klimple, the graduate student, is seen here, standing on the left side of the truck, or our left, and Jessica Vanderwerf Wilson, who is the water resources coordinator at the City of Edina, is on the other side, and another student, Jacob Bierman, is standing in the door. The project is funded by the local roads research board. And the administration is through the Minnesota Department of Transportation and the Center for Transportation Studies. The essence of this is adaptive management. Salting is something where it happens many times during a year, and each event is a learning experience, and we can use that to continuously improve the process. Generally speaking, the idea is that we would measure meltwater coming down the street. We've never really done a study no one has done a study that looks at the road salt on one side and the meltwater on the other. And so we are starting in a new direction here. And the idea is that we would provide feedback. We would synthesize this into snowmelt metrics. For example, later I'll be talking about cumulative degree hours. And how does that relate during a melt event to the amount of chloride that comes out? Those kinds of metrics we have shared with the Edina Public Works Department, and then they process that, think of a new way of doing something maybe to lower the impact, and a new de-icing event starts. That's the idealized version. Now, it didn't work out quite like that, but it did. The adaptive management part, particularly the communication, worked out, I think, very well. This is what it looks like in real life. This is the first year workshop at the end. We had 3 workshops, one before the study to get some ideas and where to put samplers and things like that. One at the end of the first winter, this would be 2017 to 2018, and one at the end of the second winter, which was 2018 to 19. The second one was a little bit better attended. There were about 15 to 20 here. It might have been 25 at the second. And not only the operators in the yellow coats, but also supervisors and several layers of supervisors there. The idea is that we would present something. This is Melissa Fries, an undergraduate student who worked with us. She's presenting something. We did all that within about half an hour. So we really condensed down the study into a fairly simple presentation, short presentation, and we had about an hour for discussion. That's where the real work occurs. So I'm going to show you 2 parts. One, video part 1 is this one, the problem with chloride, what we did and what we found. And then the second video, which is on the same website, you should look at is the tools to manage chloride and adaptive management. Chloride has kind of emerged as a major pollutant in the recent years. Sometimes when people talk about emerging pollutants, they're talking about pollutants where we maybe really don't know the effect, but we know it's there. This is one where we know the effect. We've known it for decades. It's toxic to fish and other aquatic organisms. At a level at about 230 milligrams per liter, there's an acute standard and a chronic standard. At 230 is the chronic standard. They really don't want to be living in that environment very long. 275, I believe, is the acute standard. That will kill a fish in a few hours. Okay, so think of a number in the mid-200s here. Salt is important for de-icing. We can't really go without it very easily, without sliding around or stopping work or something like that. At least we haven't figured out a way so far. Once added to the street, it cannot be trapped or degraded in stormwater ponds or other structures. I think I've been asked this about a dozen times. What can we install to trap the chloride? And my answer is nothing economically. You can use reverse osmosis to concentrate salt and clean up half the stream, but that's something you do for under a sink. You can't do it in a catch basin. It's just not practical. Chloride also moves easily through soils and into groundwater. This is something that is showing up in the Twin Cities area, and we'll talk about that. And as I said, it's toxic to fish. And the drinking water standard is 250 milligrams per liter. So I've thrown out three numbers to you: 230, 250, and 275. Okay, Minnesota's chloride problem. Chloride in surface waters has been moving mostly upward. MPCA measured 111 surface waters where they had 10 years of data. 60 had increasing trends. Most of these, but not all of them, were in the metro area. 50 had no significant trend, and only one water, and that was outstate, had a downward trend that was significant. So more up or stable, but almost nothing going downward. We also, in a separate study to develop a stormwater research roadmap for Minnesota, we surveyed all the stormwater managers throughout the state, or at least we tried to reach all of them, and they responded. We asked questions about how they perceived the importance of various pollutants. And chloride was very near the top for a lot of them. Overall, it was number 2 after nutrients, almost tied with nutrients. That's how important it is perceived today. And you'll notice that there's a lot of big dots. Big dots mean on a scale of 1 to 5, how important is it around the metro? But they're not just around the metro. The metro, the city. There's around other cities too. Here in the west, here in the southeast, here up in Duluth, in areas, and many places in the state. So this is characteristics of any watershed that has a significant amount of impervious surface. So we shouldn't think of it as just a metro problem at all. As I said, it can migrate down to water, and it's particularly a problem in shallow groundwater. There is a potential for drinking water contamination. The red dots show 230, greater than 230 milligrams per liter. The yellow are in elevated levels compared to natural background, and the greens are more or less natural background type levels. And you can see that these red dots are scattered all over the metro area, and there is significant contamination. Now let's be clear about this. So far, we have not seen a threat to municipal drinking water supplies. Those are usually from much deeper wells. These are much shallower wells. However, there is some anecdotal reporting that some people using private wells, household wells, domestic wells, have seen some evidence of increased chloride. So this is something that is happening, and among other things, and we'll talk about this more a little bit later, the shallow groundwater also becomes the base flow in streams during the summertime. So it comes out, and what is groundwater actually comes into the stream. Instead of becoming a drinking water problem, it's now an aquatic life problem. And I'll talk about that just in a bit more later. What we developed an approach for doing this, for measuring chloride and flow in meltwater throughout Minnesota's winters on a small watershed. It's just a couple of acres. And we analyzed the flow and movement of chloride in this residential neighborhood for 2 winters, 2017 to 18 and 2018 to 19. To do this, we had to develop a new kind of sampler. This is a box. It's made out of plastic. It looks a bit odd because the plastic is one that can stays solid, doesn't become brittle at 20 degrees below zero. And it's also very durable. If we drop it, it probably wouldn't break, and things like that. You'll notice it has holes drilled in the side. This is a plate that fits over an opening. It's got holes that are drilled at very specific sizes. And the reason we did that is we want to measure flow, but we don't want to have, we don't want it to flow out through a pipe or such. We want to measure water level elevation instead of flow directly because of the freeze-up problems that we might see in like a small weir or something like that. So the flow, we made a relationship between the depth that accumulates in the sampler, the depth of water, and flow rates, and we calibrate that in a flume at the hydraulics lab at Bioproducts and Biosystems Engineering. So it took us a fair amount of time to develop that. We then installed it. Here's our site, our study site. It's just a nice residential area in Edina. We found that people were rather friendly and inquisitive when they were walking their dogs and such throughout the 2 winters. We built a metal frame. To hold the sampler, we dropped the sampler, carefully lowered the sampler with straps into the basin, and here it is sampling melted water. This is the grate's back in place, and this is a dandy bag that collects the solid material, that just the rough stuff that comes into the top of this sampler, and would clog it up if we let it go in. It also keeps the water flowing into the sampler, not down the back side of the grate. So there it is in place again, a little bit closer view. And there is Doug. We are doing sampling snow cores. We developed a little snow core sampler for this thing. And we are sampling along a gradient, about 6 sites. We go out about 20 feet or so. We collect those. We melt the samples inside that coring tube. And we measure the conductivity of the water and the amount of water and such, and calculate a mass of chloride that goes into pervious surfaces, meaning lawns, mostly lawns in this case. Now, this is probably more data than you want to look at. I just wanted to show you what one event looks like. The first top graph here is simply temperature in red. This is a melt event. It's going up to 45 degrees and then coming back down, bouncing up a little bit, maybe just above freezing again, and coming back down. So one way to integrate the effect of temperature is called cumulative degree hours. So a degree hour, if you have 1 hour in which the temperature is 34 degrees, the freezing point, of course, is 32 degrees. So that is 34 minus 2 times 1 hour. That's 2 degree hours. If you have the next hour, it's 40 degrees. Well, that's 8 degrees over freezing, and it's 1 hour. So that's 8 plus 2, that's 10 degree hours. So in this 40 hours or so that we have tracked, we build up about 20 degree hours. That happens and stops. There's no more accumulation here. It just stays here. This is the maximum right here. And that happens right as it drops below 35. And then there's no more melting going on. Second graph shows what happens to the meltwater. This little number here, I think that's an aberration. I think it's probably more of a continuous peak here. But I didn't feel that I could just take it out either. But basically the flow happens at about 15 hours, as you can see. The flow is, between 10 and 15 hours. That's right in through here, right before it freezes again, and then the flow goes way down. One characteristic of melting snow piles with chloride in them is that the chloride eludes out. That's E-L-E-U-D-S. It's a process called elution. It happens, we know that happens in snow piles. The saltier water comes out first, and it kind of takes the chloride out of the snowpack, and the last part actually has very little chloride in it, if you have a big snowpack at least. And then we calculate the mass. This is in pounds now per hour, the mass of chloride that's been taken out each hour. And this event looks like it's probably about 100 hours or so. It was one of our larger events. And that's a kind of, from this, we tried to develop metrics, like, as I mentioned, the degree hours, cumulative degree hours. We've pounds per event, so we've summed these up in C there. We've summed it up. Like I said, I think that's about 100 or so hours, but we sum that up. That becomes a metric. The total inflow into the meltwater, so it's outflow from the street, inflow to the meltwater sampler. That is a response metric. Then we have input metrics like the amount of snow for the previous days, the amount of rain, and things like that. We had a very hard relationship developing statistical relationships between external drivers like temperature and response variables like chloride loading. We did find some, but not as many, and not as many related to the chloride itself, mostly related to flow. For example, the more degree hours, the more total flow there is. That's something you would probably expect. But we did find that chloride, the cumulative chloride load. So what we did, we took every hour of the whole study. This is a huge spreadsheet, thousands of data points. We took every hour of data, and we calculated the chloride loading, and then we ranked those chloride loadings from top to bottom. So what was the highest chloride load per hour, and then all the way down each hour, and then looked at how much cumulative loading there was as a percentage of the annual total. So we added them all up all the way through the year, got a total, and then for each event, starting with the biggest event was so much percent, second event added so much more to that, and so on and so forth until you get to 100%. So these cumulative curves, cumulative loading curves, mostly have this kind of a shape. They go up and they reach something, this would probably have to reach 100% somewhere around here. But look at what we found here. This is winter 1 and winter 2, but the results were pretty close. To reach 50% of the annual chloride loading, you only needed about 48 hours, less than 50 hours, 2 days. Okay, now that's not 2 contiguous days. That's 48 hours spread out. It might be 1 hour here, 1 hour here, 1 hour here, and so forth. But it did tend to cluster a little bit. But in the amount of time when you're actually having a lot of chloride going out is really very small. And we had 75% of it coming out in about 100 hours, or about 4 days worth of, if that were about 4 total days coming out. So a message from this study is that chloride loading occurs in very short bursts. It's not spread out across the whole year. It occurs when you have these large melt events, and particularly these winter mix events where you might have snow falling. You might have 10, 20 inches of snow. I'm doing this in late February. You might have 20 inches of snow between now and the end of March. And then that accumulates, it melts, and then it freezes, or worse yet, it rains on it and makes it melt even faster, and then freezes, and you've got this layer of ice that is very difficult to deal with. But those kind of winter mix events is what we're talking about as being the primary sources of chloride. When you look at the whole year, that's where most of the chloride comes out, or the biggest chunks of chloride come out. And to make this a little bit simpler, here are some of our top events. So at the most, we had about 120 maybe pounds of chloride in one event. We had about 9 events that were over half the chloride, and really it's more like 4 or 5 events. These other ones are rather small. So again, a lot of chloride comes out during these melt events, mostly associated with a winter mix. And the other event is just the end of season snow melt. It might be a big snow and just everything melts at once and it's spring. So we're developing a picture of chloride. We're not there yet. This study, we've gotten as far as we can go, but there is a cycle here. We are trying to figure out how chloride moves through watersheds. We know the plow-off takes off a considerable amount of chloride, moves it into the snow piles. Some of that melts back and is some of that chloride that comes in when it starts, the temperatures warm up and such. Some of that goes, the meltwater goes to infiltration. As I said, chloride goes right through soils, and it can end up in groundwater. We are going to look at that in the next video. We tried to develop a modeling approach for it. We don't have it fully calibrated. And then we have meltwater from the street itself. And of course, I couldn't put the arrow under the truck quite, but we're also dropping chloride onto the streets throughout this whole process. So this is the end of this video. And in a few minutes, I'll start another video. And this will show up as 2 videos on your website.